Okay, well, it is past 14, so we'll start because we have to start someday. Um, yep, this is can data-oriented design be improved? Also, it's college in where I live is not the same ages as in the United States, so it's not a great indicator of my age. If you want to know that, come and ask me after the talk. Um, okay, so we're going to start with a brief history of programming languages because it'll be useful at some point. Um, well, back in the days where my dad was born, so somebody invented Fortran because they thought that writing assembly was really painful, and somebody thought that writing Fortran was really painful, so they invented Lisp. Um, these two languages are like really far from each other because Fortran is structural and really imperative code that is similar to C in some ways. It's not C because otherwise we will still be using Fortran. And Lisp uses a functional approach, which is, in my opinion, much easier to teach to people, as teaching the Lisp syntax is like the most simple thing ever. You have a parenthesis, a function, arguments, the end. That's the whole syntax of the whole language. If we could have that in C++, it would be like the best day of my life. After some time, people thought that using Fortran was kind of bad, which is true. And they invented object-oriented programming, structural programming, and modules in a way to separate the code to make it easier on large-scale projects. Because writing Fortran is not necessarily great at a large scale. Although Fortran also has like revision. Like there's Fortran 2018, which has object-oriented things, and it's another language. It's like C++ 98 versus C++ 20. Completely different languages that some people think they are the same, but they aren't clearly. And in the 2000s, people started to do template metaprogramming and concurrency because, well, somebody figured out that there's a maximum performance you can grab out of a single core on a computer. So they just said, okay, well, put a bunch of them one besides another, and it's going to make us much better programs, which is true when people actually achieve it. And now we have a problem because in 2020s, we don't have anything really because, well, we're 3 years into it. So we have to find something one day. Okay, well, this talk is about improving data-oriented design. So we got to understand what it is, or at least the definition we're going to use for the duration of this talk. Some people may think it's about optimizing cache lines and struct layouts, and well, it may be when you actually write the code, but it's not the principal philosophy of it, at least in my opinion. Wikipedia says that it focuses on optimal transformation of data and focuses on modeling programs as transforms, which is true to a certain extent. As well, yeah, that's pretty much it. I think. Okay, so we're going to simplify the definition because we can have a lot of things with the way you think about the code and such. So let's do a minimalist definition. Data-oriented design at its core is just having a function treat some data and spit out some output. Like, it's supposed to be all programming apart from object-oriented programming where you model the world for some obscure reason. And in data-oriented design, we put a heavy focus on the data, because that's in the name. And a lot of optimization techniques that come with this are about looking at your data. What do you have in your problem? Do you have like a sparse set with only zeros? If for example, if you're sorting something, if you're sorting an array that's almost all zeros and like 3 ones by a million elements, it's not going to be the same solving of the problem as if you had random values that were uniformly distributed. And this is pretty much what is most important to, at least for this talk. The only problem is people don't go too deep into how things work, because they have limited time and they look to write code as efficiently because they have a boss who wants them to work at some point. So data-oriented design code is not necessarily close to what the philosophy is. This is controversial. Usually, when I've seen data-oriented code, it was platform-specific code because, well, you need it if you want to. You can't code in the data-oriented design philosophy. You can't code without knowing on what platform you are. Coding for a 6502 is not the same as coding on a modern x86 machine. It's also going to look like procedural and imperative code because you want to have that control over every part of your code. Otherwise, you lose the control of your data and of what you're doing and of every optimization that's interesting. You're going to also have dataset specific code for the reasons I already said. And well, you're going to optimize cache lines at some point because that is what people think it is. Well, some people. Hopefully not a lot of people here. Okay, how can we improve it? You can ask ChatGPT. I'm a student, so that's what students do nowadays. But ChatGPT is not really helpful in this case. It spit it out like a 10 times longer answer. But most of the things were like, look at your cache lines. Yeah, I know that's the thing I talked at the previous slide. I don't need to repeat it. So I only took the first advice it gave, which was using modern C++ features, which is not really liked in a bunch of places where data-oriented design is used. I've seen a lot of people not necessarily be happy about the implementation of stud PMR and this sort of stuff, but we'll take it as a note because maybe artificial intelligence is superior to natural intelligence. Okay, so let's do a second try because this wasn't really successful. This is a reminder of the philosophy, but what if we looked at an opposite philosophy? Because we might as well go completely opposite to trying to find something that would be of interest. Let's go back on this. That is not also just applicable to programming. Please go look at people who don't think the same way as you do, because it's really horrible to meet somebody who just thinks in one way and is completely focused on this one way, and every time you try to bring something new, they just say, no, my way is best, and that is all. If you're that kind of person, please go out of the room or something. Yeah, okay, so the opposite of the philosophy. We looked at what data-oriented code looked in real life a couple of slides ago. So let's compare it with what would be the opposite. Well, if you have platform-specific code, the opposite of this would be cross-platform code, because that's the point of it. Procedural/imperative code. would be declarative code, because in imperative code you write, you tell the literal instructions you're gonna do. While in declarative code you like apply like you apply like a filter, and you describe the process of solving the problem. Yeah, if you have like a dataset specific code, for example, like the sort I was talking about a couple of slides ago, well, the point of would be to a generic version such as like std sort, which would have none of the optimization for a specific data set, because you can't inspect the data set you use at runtime when you're at compile time, at least not for now. That may be interesting in future C++ revisions. And well, every like struct layout and cache line optimization would be delegated to the compiler, because you don't want to actually deal with this. You just want to apply your code and say, okay, I'm doing this, so let's filter this array and let's put a map on it or something. And filter and maps and transforms and, well, stud transform and this sort of stuff really sounds like functional programming. So let's look at functional programming while we're at it. What is functional programming about? It's about chaining functions to make program. You take your data, your vector, your whatever you have, you put a filter on it, you filter out the bad bananas, and you map it to something which smooshes the bananas and stuff like that, until you get something that does something. Well, if you look at that, if we chain a bunch of functions, we could just also combine them and have a single function, because you're going to have a main entry to your function, to your program, not to your function. And well, if you have a main, hopefully the programs you write in your life do something. So you're going to have an output of data at some point. Otherwise, it's just burning a CPU, which is cool, but not very useful. At least that's if you're not like actually purposely wanting to burn CPUs of people and increase the global consumption of energy and accelerate climate change and kill us all. But yeah. So yeah, okay. This is maybe too fast. This is the exact same formula we already saw a couple of slides ago. So we can say that data-oriented design is the exact same thing as functional programming. But it isn't, because we have seen also more slides ago that it was completely opposite, and one was generic and didn't care about necessarily the layout of the data and all of this, while data-oriented design is focused on this. But in this formula right here, the only thing that changed, the only thing that changed is that instead of focusing on instead of focusing on the data, we focused on the function. Otherwise, it is the same. Yes, there's monads and a bunch of stuff people made up to look intelligent or something. I still don't understand monads. Don't try to explain them to me. But in the end, it's at its core, and its philosophy is the same, because we're trying to make a program. And this is also advice for humanity. We're all humans. It's not because somebody believes in something or has a specific color of skin or sexual orientation that you're not human at all. And in a way, this is weird, because object-oriented programming is a very huge paradigm in the industry, but it's really not about getting data transformed and from one point to the other. It's more about, well, this is a cup. We can put water in it. There's the put water method, which I should probably do in not a lot of time. And it's about modeling how the world works, especially when you're in languages such as Java and C++. It's really, in my opinion, kind of exaggerated. Yeah, okay. So what can we grab from functional programming to bring into data-oriented design? Because we have to grab something at some point. Otherwise, we're not going to advance and we're not going to go anywhere. Well, we can't go in extremes because, well, if we go all the way on data-oriented design, well, great job, we did exactly nothing. And we can't go all in on functional programming because I'm sorry, but I don't want to ever see the code that I saw in this talk. It solves a problem, but it's horrendously complicated. And for something that you could have made in a couple of lines, I don't personally see the point, but that's controversial. People aren't going to like that. And while I did, if we want really to have like a lot of functional things and implement everything with standard algorithms and basically rewrite in functional programming all of our programs, then just use Haskell. It's going to give you a much better experience than trying to do it in C++ because, I don't know, maybe it was kind of designed for that. Although Haskell is hard to teach because it's really like functional all the way. While in Lisp, which I like way more, in Lisp you can do some things that are less, more understandable for the average like C programmer, and for the average person too. Okay, what is available in C++ for functional programming? Because we're not at like dconf or something with our CppCon, and we want to do C++ at some point. Well, in code in quote-unquote runtime code, we can do lambdas. We can return functions from other functions, and we can do a bunch of stuff with this. Lambdas are probably the most used thing of functional programming, even though you don't necessarily realize it when you use them. We have a bunch of algorithms, 105 before C++ 20. Now I don't know what's the number. There's a lot of them, but it's not really interesting to learn them all, apart from if you have a lot of time to waste. We have ranges, which are extensions over STL algorithms. And they also contain new stuff such as like zips transform and a bunch of stuff like that. Although ranges in the context of data-oriented design is maybe not appropriate, because if you use the lazy ranges, you have like a certain state that must be transmitted, and some people say that they don't use ranges in like high-performance situations because of this. I don't have that much experience in that domain, but I'll believe them. And yeah, we have function pointers, so we can take functions and do all of this kind of stuff. Okay. In compile time code, we have templates. And templates take types. Types can be manipulated to a certain extent. You have just in the standard library, you have like remove cvrft and a bunch of these sort of functions that manipulate the type you're using. But what I want to get to is that it's not just about removing an ampersand after your type. You can do much more, and you can manipulate them and move them around. So we can apply these ideas in our code and in data-oriented design. But we're starting to get far. If we're going to get far from data-oriented design if we start putting a bunch of stuff that is functional. So let's find another name for it. Let's do transformation-oriented design, because we need a name. That's the only reason for it. Okay. Well, one thing that is important on this slide, sorry if you try to take pictures of the last slide, is the runtime code is not necessarily important, especially since we're like in software design code track. So we're just gonna keep the compile time aspect of functional programming, so manipulating types and doing what we want with it. There's the definition, and we could keep, and we must keep focus on transformations, because that was the original point of data-oriented design. And if we go away from this, we didn't solve anything. We just created another thing that nobody's gonna probably use ever. Okay. Now that we took that idea, let's try a third time, because first time is the charm. So we're gonna look at another opposite of our concept, because created sort of another concept, and it worked one time, so why not two? A couple of slides ago, I was arguing that object-oriented programming was really weird because it was not at all the structure of all the paradigms we looked at since the start of this presentation. So maybe, because it's so far away, maybe it's an opposite. So we may be able to grab some things from it. So we can grab some things from it before it dies. That's pretty much it. Okay. Move. Because we need some examples of concepts, we're going to look at an example where like an image loading library. Because image loading is used in like many industries. In video games, it's used to load textures and normal maps and all of this kind of stuff. In cinema, it's used, in digital cinema package are just like JPEG 2000 files that are packaged and displayed to you in a big projector. And the worst is the resolution is not even like that interesting. It's like 1920p, 1080p, which is 2K DCPs, and 4K DCPs are 4K. But yeah, that's another thing. We could use it in Earth remote sensing, because that's useful for weather forecast and a bunch of stuff. And we could even use it for saving lives, because medical imagery is much of a thing now that we have computers. One of the other reasons that it may be an interesting case to look at is that image concepts are varied enough, because it's a file, you have chunks, you must load them, you have many different files, possible files. So it allows us to cover a wide enough gamut of problems so that it looks like a real software. Okay, so let's look at a traditional OOP approach, because we're trying to look at that since a couple of slides. In traditional OOP fashion, we would do a base class, which would contain stuff such as like a method for loading and a method for identifying the file, and potentially a data structure to store the things you're loading. Because if you're not storing anything, you're not doing anything, and you gotta have a data output at some point. Yep, we're gonna have a signature. It's gonna hold data. Then we would derive class that would implement loaders, because well, there would be virtual methods and all of that. So they would implement like a PNG loader and whatever. And if you and we will. It will also hold like specific data to that file. For example, if you're loading a JPEG file, you would have like potentially EXIF metadata. Well, PNG also has it in a special chunk, but some other file formats don't have it. Yeah, but this has downsides, and this is the reason like OpenImageIO isn't used in every software imaginable, other than it being a very huge dependency. If you use virtual functions, you're going to have vtables and virtual calls, which is a no-go in many code bases, especially code bases that are interested in data-oriented design. It's not particularly flexible, because you can't like have the data propagate and have like generic data. For example, for EXIF metadata, you can't really have it come from the base class, because it's not something that exists everywhere. And okay, you could do a more complicated architecture and have like EXIF image file, and it would be really messy really quickly. And yeah, it's not only like virtual calls. If you want to access that spatial data of certain files, you would have to do a dynamic cast, which would be horrible, because ew, that's the only reason. And yes, you're locked in a, as I said, in the design of the base class, because that's the point of how inheritance works. Okay, so how would it work in the weird thing we're creating? Well, we wouldn't have any base class, because we don't want to inherit anything. So instead, to replace it, we group them in a list of, well, types, because we implemented them in types before, so let's keep them around for now. And we'll have a list of type which we could iterate over, because that's the point of the list. And because we also killed that base class, we don't have, it's no longer like linked with any data, because the data doesn't come from the base class. And we basically only have functions. Yeah, yes, that's it. We basically only have functions, because the loading happens and it returns you what you want, because the function that loads is in the file, and you understand the point, I think. Okay, so let's calm down a little bit, and let's compare OOP and the thing we're creating. What unites all the classes in the OOP is a base class. That's the point of inheritance. While here, it is a type list of said transfer packages, which we'll look at in the next slide. Derived classes and packages are in OOP really built around the functionality of the language, while in what we're doing, not linked to anything because they're standalone classes that just float around somewhere. The data is not associated to the class because it's just a grouping of functions, while in OOP you have the data that comes with your object. There's no virtual calls, no dynamic cast, so that's cool. While in OOP you're locked into this because it's how somebody designed the language 40 years ago. And we have more room to move within the methods of the functions we're using to load our images and such. Okay, I talked about transform packages. So we must define it. Transform packages, at least here, will be a class that contains static functions, transformations, and that group functions together. It will also contain like using definitions because usings are basically just variables that context per variables that contain a type in a sort of way. It may contain enums and some other static data for example, if we were actually implementing an image loading library, we may have like data that says, okay, well, this file has this magic number, so you could like just look at the magic numbers and say, oh, okay, it's this file. And if it's not, you could default back to going to loading it in a less efficient way with a method that would tell you what the signature is. The point of them is not to be manipulate. If I can pronounce a word, it would be better. They only are manipulatable at like compile time. Otherwise, it wouldn't make really much sense. At least in the context we are. They're not instantiable nor destructible because it still wouldn't make sense. They're just a grouping. It's like a namespace that you would have put function, and the namespace would be like passable everywhere you want, which would be actually a cool functionality. We should look into that. But the last point is important. You don't need to use that definition exactly. You don't need to put every destructor and constructor to equal delete just because that's what I wrote on my slide. You could just leave it alone because anyway, if you use it right, you're not gonna have this sort of stuff. Yeah, that's pretty much it. Okay, what does our design change now? Well, we created. Oh my god, this slide is wow. It's not a straight line. Huh? Can I have like a? Yeah. Oh, I can have a pointer. Okay, that is here. So we just look at this, which contains the implementation of specific transformations. And for example, if it would be in image loading, it would be the implementation of the file loader. The library would implement. It would implement all of the managing hey, does this file, is this a GIF file, is this a PNG file? It would handle all of this using the packages and specifications we define here. And well, it's a library, so it would contain probably some other utility functions or whatever is necessary to make it work. And well, in the user side code, it would look like just calling the function, and you would have to explicitly pass in your loader specifications when you call your function. And the user side code would just be defining, well, what transformation am I gonna do, because that's what it is about. Yeah, that's not right. It's and we will also abstract away from every file type, because we package them in under our library. We won't have to document that much things, apart from how that library works, exactly what methods it needs in the packages, and well, how to call the method, what arguments you would pass. For example, if you would have, well, set image library, you would have something to ask, hey, could I have like RGB data, and could I have like the dimension of my image and stuff like that. And we would also have modularity, because all those files are completely detached from each other, because we don't inherit from any class. They don't rely on anything that is from the library. It's just the implementation directly. Just as if you wrote standalone functions. Okay, so I assume you should be able to understand what I'm saying. If you're not, then that's just because it's my first talk and everything that comes with it. And in a nutshell, the philosophy that we're describing is just, firstly, having the packages that specify the way you want to do the transformation. Having, after that, set compile time for functional programming, because you want to have to be able to manipulate the packs of the function you made. You want to be able to manipulate them to load them in whatever order is more optimized than the other. And well, use modern C++ features, because that will help with organizing things. Maybe artificial intelligence isn't that bad after all. My teachers don't think it is very good. Okay, so we should be able to write code. So this slide is named "Let's Write Some Code." But the code that I wrote, I'm not proud of it. It's really kind of horrendously bad. So we'll skip over the next slides really quickly so that I don't have to suffer that long. The objective that we have for the code. We want to replace hard-coded send switches, because in our image images library, we have to like switch over, well, what file is it, and we have to look over every file, and we don't want to hard code in well, let's do the test for TIFF, let's do the test for PNG, let's do the test for that is long and really unmaintainable code. And this is also the reason, like, there's this image loading library called STB image. It's quite well known, and it's written in C, and they don't have concepts or modularity like that. And one of the reasons we don't want to add new file types is because we don't want to increase the burden of going manually and adding in every single place of the code so that it works everywhere. Because if they don't want to update the loaders and stuff. Yeah, we will need to be able to call function only if they exist, which is a hard problem which I don't have a solution that satisfies me. Ideally, we would want to do it without reflection, because if we can use what we already have, it would be kind of great. Since C++ 17, there is this thing called void t, which I still don't have a hard grasp over, but it should be able to do what we want to do. But we also have concepts in C++ 20, so we may be able to mix and match them. Not in this, because the code is horrendous, I already said that. Okay, so close your eyes now. Okay, so yeah, we need to know if something is in a list of types. This is not pretty. Go look at the talk by Andrei Alexandrescu on variants. He implements it in a much nicer way. Although it won't work in it is less easy to use if you're like in if constructor statement than this, but this is not very good. And as I said, the point of it is not to show some code, it's to show a philosophy of how to structure said code. Okay, so this is getting worse. This is not good. Yeah, no. This is supposed to represent what an image loading library would look like. But there's a bunch of stuff that hasn't been being touched in like a couple of weeks, so that's not really good. That's what happens when you never made a talk in your life. But there's still like the general building blocks of an image loading library. In an image loading library, we would have something like a signature to be able to, well, it would not be called that because that doesn't make sense, but we would have that to identify. It will return a bool to say, hey, can I load this or can't I load this? And this would be a loader which will do some stuff and will take as arguments a list of requests such as RGB values, do I want EXIF data, and this sort of stuff. Okay, this is the curse code. There's a macro, so people are not gonna like it. We're evolving back to C. This is not the right direction. The point of this is to try to make a call only if the function you pass in the macro exists, but you have to define it before. It's really not clean. If somebody has a solution, please give it to me, because my eyes bleed every time I look at this. If you want bad code to show it to your boss and say you write good code, take that slide and show it to your boss. He's going to be, or they're going to be really happy about it. Yeah, the thing is, we can use requires here because we're in this function, so it will probably work. It will work if you define the function here, and it will like switch at compile time so that it doesn't call if the function doesn't exist. It shouldn't work, in theory. Practice, that's compiler dependent. Yeah, no, this is dumb. We skip it. Okay. Well, no, we may not want to skip the last one actually. Okay. Switches in the way we implemented them in this library. Well, that wasn't the library, but that's not the point. We're just mapping from a variable to a quote-unquote type. Put big quotes around that. Because a type, as we saw, it can hold the data, and well, it is data, and it can hold functions and such. So it is just mapping from that to a function in a way, though it is really philosophical and not really. This is more philosophical than actually ingrained in what the standard says, but hey. This is just a search. This part is just a search implemented in a really bad way around the type list. Basically, you go and you look at the index, and then you do -1 until you made all the elements. This is probably the best code of the presentation. You need this because you need to be able to iterate over all of the types that you have that you could possibly load. Yeah, that's all. Yeah, well, that's pretty much it. That's not really clear. I think I'll go grab a look at something else after. Okay. How could we simplify this, and how could we make the code actually enjoyable to look at? Well, this may be achieved through proposals such as tag invoke or meta classes or static reflection. Tag invoke, I don't think it solves the exact same problem. Static reflection, static reflection would solve this problem, but it would also probably bring a bunch of other problems of abuse of it, because it's something that could be really easily abused. And meta classes, well, they in a way do the same thing, but in an inverse way. We need to have better ways to manipulate data as types as data. Because currently the code is not clean. We need better ways than this. And perhaps the answer would just be to steal what André Alexandrescu already said in his talk on variant and create a stud type sequence with a bunch of stuff around it, such as, well, you would need a head and a tail method because functional programming. That's pretty much it. Okay, what can we take away from this? You're not the one writing the code. You're writing instructions for the compiler to write your code that is going to be in a flavor of assembly. This allows you to think about the code is just something you can manipulate and move around, and you can ask the compiler to do it for you. This is probably the most important thing of this talk. It allows you to have easy modularity, easy with huge quotes, easy modularity, and it's really a key to quote-unquote better design, at least in my opinion. Optimization is done at all levels. It's not just about cache lines and stuff like that. It's about structuring your code in a way that allows you to make it maintainable, because there is also an optimization of the time. You don't have infinite time to write your software. And yeah, if you have a problem, look at opposites and try to find similarities, even though something may be different in what you're looking at. Conclusion, finally. Did we improve data-oriented design? I don't know. I think what I showed addresses a different level of problem solving. It addresses more of software design than really how you're going to write your code at a function per function basis. In fact, if the talk was about that, we would have looked at the implementation of an image loader, but we didn't. But one thing that is great about this is that it's compatible with other paradigms. So if you write, even with the templates and curse stuff, you can still write the inside code in functional programming. You can still write it in data-oriented. You can still write it in, God forbid, object-oriented code. So it isn't really putting a burden on your design. And you can use it in your code starting from today. I don't encourage it, but you could if you really want to make me a favor or something. It doesn't need to be about templates. The three concepts here are way more important than the horrible template stuff. It's about structuring your data. It may be even implemented in a completely procedural way. It's about structuring your data in a way that allows you to make more modular code in the end. That's one of the main points of it. Yeah, so maybe we may have found what those question marks were, but that's not for me to decide. That's for the people here to decide. Thank you.